So the next speaker is Jim Hurrell. I see him standing right here. Jim is the director of NCAR and a senior scientist at NCAR. He also spent a year at the Hadley Center, so there's some symmetry between the first two speakers and their careers, and they both have served on the COLA Scientific Advisory Committee. And Jim has been involved in development of CESM. I was co-chair of a natural variability working group with him, but that hasn't been held against him apparently. And he's going to speak on strategic priorities for NCAR, development of multi-scale simulation and prediction systems.
Thank you very much. I'll give you 20 minutes. Give me 20 minutes, okay. Does this count against my time? All right, so I want to begin by just really expressing my sincere appreciation to Jim Kinter. Take your seat, please, Jim, for the opportunity to participate in this wonderful event. And Shukla, I've been a longtime admirer, haven't had the opportunity to work directly with you, but certainly recognize your influence and your advocacy for our field and the international cooperation, the international programs, the leadership you exhibit on so many levels. And it's a great pleasure to be here and participate in this. And Ben, I don't know, do you have to be a COLA employee to give Kinter a hard time? Because Jim, I just want to say, thank you so much for slotting me after Julia and putting me in a session with Julia and Ramaswamy and Tim Palmer and Dave Randall and then Jim Hurrell. I mean, thanks a lot. So for this, I'm pleased to announce to everyone that you were appointed to the NCAR advisory panel as a result of this great favor you've done. So in this session on next generation modeling, indeed I thought, given my role at NCAR, what I thought I'd try to do is just give you a feel for some of the directions we're going in terms of modeling and climate modeling in particular, given the relatively short speaking slot here. And certainly the points we've heard throughout the day, the points that Julia's just made, resonate very strongly. And as I think about this strategic plan, I've been director for about 1.5 years, and when I step back and look at this strategic plan, one of the reasons that I thought that I would talk about this a little bit is because I think it's a strategic plan that we have at NCAR that Shukla would resonate with. It's a Shukla-approved strategic plan, I would venture to guess, and I'll try to explain that in a minute. But I think it also reflects the influence of so many of the people in the audience here, people that have been involved in the World Climate Research Program, the World Weather Research Program, programs like CLIVAR. You know who you are, and you've all had a tremendous influence on my thinking about these kind of problems, and I've had the opportunity to put my fingerprint and shape some of the directions we're taking at NCAR, and I suspect you'll see a reflection of that. So at the National Center, of course, we do everything in collaboration with the community. A fundamental aspect of our mission is not only to advance research, but also to support, enhance, and extend the capabilities of the broader community. And so our strategic planning definitely involves a considerable amount of community input. Once again, I received no more input from the community, any individual in the community, than I did Jim Kinter. Sent me about a 10-page commentary on the strategic plan. Another reason that you're now on the, I did ignore most of it, but that's okay. And our strategic plan, and I thought it fit really nicely to the theme of this meeting, is to focus on a couple of grand challenge problems. And both of those grand challenge problems really involve predictability. The first is understanding and improving our ability to predict atmospheric, chemical, and space weather hazards and understand the impacts of those hazards on people, society, and the environment. And this includes, for instance, not only understanding the processes responsible for hazards, but also the global context in which these hazards occur. And the second grand challenge problem is the understanding and the prediction and the projection of both natural and anthropogenic climate variability and anthropogenic climate change from scales, from global scales down to regional and even local scales. And in that strategic plan, if you go to the main webpage of NCAR, you can take a look at this strategic plan. I encourage you to do so. These are some of the themes, and these are some of the themes that we heard Julia talk about. And the one that I want to highlight here today, we're doing things in terms of big data. We certainly recognize the importance of observations and talk about some of the key process level understanding that's required, some of the instrumentation that NCAR can play a role in terms of next generation instrumentation. But we're really moving again in collaboration with this broader research community toward more unified modeling approaches, beginning to bridge the historical gaps between the numerical weather prediction and the climate simulation communities, as well as I think Hania and a few others made some really nice comments this morning about data assimilation. And data assimilation is a tool not only to generate initial conditions, but a fundamental component of improving and understanding modeling systems. And this is one of the areas within NCAR that I'm really trying to emphasize, and we've created a new data assimilation program, but I won't say more about that at this point in time. So an aspect of all of this is really an effort to develop and support for community use global modeling systems that run efficiently, and the challenges of the next generation architectures are definitely out there, as well as accurately at a variety of horizontal resolutions, because we're supporting a broader research community, but as well as developing global models with limited area, high resolution grids for both regional downscaling, but also the upscaling of smaller scale, mesoscale influences back on to the larger scale climate. And so this is very much an area of emphasis. I think this is absolutely required for problems like this, trying to assess the local impact of global trends in climate, as well as, again, speaking about some of the biases and the errors that have plagued climate models for many, many, many years, decades in many cases, is what we've heard in this symposium so far today, the upscaling influence of key smaller scale processes. And these kind of capabilities are absolutely essential to do things like tropical cyclone forecasting and to understand how tropical cyclones are impacted and influenced by changing climate conditions. And it's also really critical, I think, in order to fully exploit all of our observing systems. And again, this theme of data assimilation is very central to the directions we're moving at NCAR. So, Kentor also taught me that if you don't have a lot to say, at least you can wow people with nice visualizations. So here's another example of that. This is a slide that I often show. Of course, as I've said, the role of NCAR, we have more than 35,000 registered users around the globe of our community modeling systems, our weather research and forecasting model, as well as our climate models. Many more users than that of the data. And so again, I really want to just indicate to you some of the directions we're going and some of the capabilities we have. What you're looking at here is an animation of the total moisture content in the atmosphere from one of these community data sets that is available for you to download and take a look at. This is from a 100-year coupled simulation of our version 1 of our community Earth system modeling system with about a 25-kilometer atmosphere and land system coupled to a 1/10 of a degree ocean model. And it's a very rich data set, many aspects to look at. I'm not going to spend very much time on this slide. Again, at the top is a link. I would certainly encourage you to take a look. This data is freely available from this 100-year simulation. You're looking at annual mean biases in the sea surface temperature field from this high resolution run in the top panel compared to the standard version of CESM, and Ben illustrated some of the improvements that we've seen in this community modeling system in the lower diagram. In general, you see a better simulation of the sea surface temperatures, reduced biases, especially in the central and the eastern tropical Pacific Ocean. You still see biases. But you see some significant improvements in areas where you perhaps would expect that resolution really begins to pay dividends, such as the upwelling regions off the west coast of the continents here, the Benguela Current, and you can see the presence now of a cold tongue in the equatorial Atlantic, so at least we're getting the east-west gradient correct now. This has benefits for the simulation of rainfall in this region, and I think it's very important for many applications. We're not only looking at mean fields, there's a lot of diagnostics out there. This is just one of those. This is looking at the simulation of ENSO. If you look at the standard deviation of Nino 3.4 sea surface temperatures from this high resolution run, I think it's around 0.68 degrees Celsius over this 100-year simulation, which of course compares quite well to the observed magnitude of Nino 3.4 sea surface temperature variability over a shorter instrumental period. But it's about half of the amplitude that we saw in the lower resolution version of the model. So there's some intriguing aspects to this. And then going back to the presentation that Ben gave, he talked about these simulations that were done in collaboration between NCAR and COLA. I know Ben and Jim Kenter and a number of people at NCAR were quite involved in this. This is actually from these older PetaApps runs, but we see very similar results in our new high-resolution version of the model. This is looking at the simultaneous correlation between the surface latent and sensible turbulent heat flux and sea surface height, which is a proxy for the ocean heat content. The reds indicate positive correlations. Beyond the strong ENSO signal that you see, you also see positive correlations in the Antarctic circumpolar current, in the Kuroshio and the Gulf Stream extension regions. Ben gave some very nice science examples for why this is important. You don't capture that, as he alluded to, in a lower resolution version of CESM, but indeed in the higher resolution model, you are capturing these features. So some of these fundamental smaller scale oceanographic features, Julia, I think, no, it was Ben also that was showing the response of the rainfall field to this, and that's very critical. I also want to point out that in addition to moving toward higher resolution in a global context, we also have some very nice data sets as an outcome of this large ensemble project. We spend a lot of time in the community talking about, for good reason, reducing model uncertainty, reducing or trying to understand and deal with forcing uncertainty. But of course, and another theme of this in terms of predictability in the midst of chaos is the very significant uncertainty that arises from the internal variability of the system. So to help the community address that, we've produced a couple of very large ensemble projects. In particular, I'm going to show a couple of results from this 40-member ensemble that covers a period from 2000 to 2061. Clara Desser, Grant Brandstatter, who spoke earlier today, and a number of others have made good use of these ensemble simulations. You may well have heard some of their presentations. This is the general experimental design branching off from a 20th century simulation. We force an ensemble of 40 fully coupled runs with the identical initial conditions in the ocean, the sea ice, and the land state, but with slightly different atmospheric initial states. These are run forward in time under the older A1B greenhouse gas forcing scenario. And I've been doing some work with Clara and others, building on some of her earlier analyses here, looking at projected changes in European climate. Just going to focus, for the purposes of this presentation, on winter surface air temperature trends between 2010 and 2060. There's a lot of figures here. This is just the 40 members of the ensemble, looking at a very simple metric, the change in temperature, the simple linear trend in wintertime temperatures over this 51-year period. You see that pretty much all of these ensemble members project warming. But if you begin to look at the details, for instance, if you just look at two of these ensemble members and look over Northern European, the Scandinavian region, where Leonard lives, you see that there's very different responses. For instance, ensemble member number 10 has a very small amount of warming, whereas ensemble member number 31, very significant warming. And we can estimate what the contribution of the so-called internal or natural variability is by simply removing the 40-member ensemble mean, which represents the forced response from the total response. This picture is showing not only the temperature responses, but very importantly, the sea level pressure changes over this 50-year period. And you can see essentially, if you will, two different phases of the NAO, even though this is a 51-year trend, but patterns that project very strongly onto the NAO. And this gives a very clear indication of the very significant role that natural variability can play, even be a signal on these timescales much larger than the forced response. And the signal is perhaps even more dramatic when you look at precipitation, where the natural variability in the system can make the difference between a drying trend over the next half century versus a trend toward wetter conditions. Just finally, just one slide to touch on kind of the range of work that we're doing. We've also produced an ensemble, a 30-member ensemble of the last millennium. This is with the standard 1-degree version of CESM, simulations from the year 850 through 2005, simulations that are being heavily utilized by the paleoclimate research community. 15 members of those ensembles have sort of full volcanic aerosol forcing, so this is just a plot looking at the year after the Tambora eruption in 1815. The literature points and suggests perhaps a tendency toward El Nino or warm conditions after a major volcanic eruption like Tambora. And so this is just an analysis of that. It turns out that 9 of the 15 runs, about twice the likelihood one might expect, indeed show El Nino type conditions. Finally, I just want to talk a little bit about some of the directions we're going, beginning to experiment in terms of, like I said, these limited area variable resolution grids that allow for not only downscaling, but the upscaling back of the smaller scale processes onto the large scale flow. These are all experiments that have been done with CESM. This is just a similar simulation to what I showed in the initial projection, but this is at the standard, if you will, kind of the IPCC class resolution of about 110 kilometer grid. And the community is beginning to do experiments with this nesting capability. I am by no means arguing that 28 kilometer resolution is the right thing you should do if you're interested in Atlantic tropical cyclones, but it's just illustrative of the capability to begin to tackle these kinds of problems. And so you can look at things like the observed tracks and intensity of tropical cyclones over the globe in the lower plot versus this one simulation where the grid is 110 kilometers around the globe, resolved down to 28 kilometers over the Atlantic region. And then you can zoom in more detail and look at the simulated climatology of the model with this variable resolution grid. And see that I think that there's quite a bit of utility in this kind of an approach. We've also done, just to make you aware and beginning to explore, and these data sets are also available for community analysis, looking at a nested grid of 6 kilometer resolution over much of the continental US. We've done a 20-year simulation of that. This is just a figure of the mean precipitation field in northern hemisphere summer. 100 kilometers in the upper left, all the way down to the 6 kilometer nesting below that, compared to observations from the TRIM measurements in the lower right. There's a lot to take in. I'm just going to point, and there's still biases. There's regions where the precipitation doesn't improve much, but just a couple of examples of where it does. From too little precipitation at the coarse resolution over a major portion of the southeastern US, to much more realistic precipitation amounts at the higher resolution due to much better simulation of land-ocean breezes. And also, if you look at the central US and the eastern Colorado region, a much improved simulation from anomalously wet conditions at the coarse resolution to much more realistic precipitation rainfall over this region in the higher resolution. And we've done a lot of studies looking at the impacts on diurnal cycle and the like. And then finally, I just wanted to just provide one more example where I think this is really important, and this is what I've learned from people like Tim Palmer and Shukla and others in this room, and this is utilizing our Earth system model in numerical weather prediction mode and testing it with data assimilation. And this is just one example where we're doing like everyone else, seeing how the model does in terms of the simulation of Hurricane Sandy. Now this is only about 4 days before landfall, but indeed there's been a series of experiments done looking at how well the model does with 8, 9, 10-day lead time initial conditions. And you can see how the model does in the lower left. This is not saying that this model is outperforming or better than any other model. Again, I'm just trying to illustrate the directions we're going and some of the capabilities that I think we're providing the research community to tackle the kind of challenges that we're talking about today and tomorrow in this symposium. So with that, again, it's a great honor to have been invited to be here and to participate. And Shukla, I'm a big admirer, so thanks for all you have done.
Question?
Yeah, Jim, nicely done. In your strategic slide, you indicated weather and space weather hazards. And I know that there's activity at NCAR with respect, and like what we're doing, we're raising the tops of our models up hundreds of kilometers to start modeling the ionosphere. Are you doing that with respect to this particular system, or are you got something separate?
We are actually. I mean, I'm not going to get into the organizational structure of NCAR, but we have one of our laboratories or observatories is the High Altitude Observatory. And one of the things that we're really trying to emphasize is the development of a atmospheric component of this modeling system called the Whole Atmosphere Community Climate Model, but -X, that's going to extend to the outer reaches of outer space. And it runs fully in this fully configured Earth system modeling environment so that we can begin to look at truly upper atmospheric processes, the influence of those processes down, but also couple that to some of the solar prediction activities and looking at CME events and the like and their propagation for space weather forecasting. So I'm talking with Bill LaPinta and others about our capabilities in this.
Okay, thank you, Jim.
Okay.